We are in section 11.11, Applications of Taylor Polynomials. The use of Taylor polynomials extends into many different areas. They are used in computer science as well as physics and engineering. Such topics include velocity of water waves, relativity, optics, black body radiation, and electric dipoles. If you approximate a function with a Taylor polynomial, there will be an error. In general, r sub n of x is called the remainder of order n. So r sub n of x is our remainder of order n, or the error for approximating f by the Taylor polynomial t sub n of x. In other words, it's the part of the series that we are missing out on when estimating our Taylor polynomial. When using a Taylor polynomial t sub n to approximate a function f, we must determine how large to take in order to achieve a desired accuracy, like what we did in the last section where it said to round things to the 4th decimal place or to the 5th decimal place. It says to determine this, we must look at the absolute value of the remainder. And so we have the absolute value of r sub n of x is equal to that function minus that Taylor polynomial t sub n of x. So at the top of the next page, it says 3 methods for estimating the size of error. One says graphing. Graph r sub n of x, the absolute value of that, and thereby estimate the error. You can use the alternative series test, which we saw a few sections ago. This is talked about on page 735 in our textbook. And this says if s equals the sum of -1 to the n minus 1 times b sub n, is the sum of an alternating series that satisfies the following conditions. So first one is b sub n plus 1 has to be less than or equal to b sub n, and this means that it is a decreasing function. Second thing is that the limit as n approaches infinity of b sub n will be equal to 0. Then r sub n, that remainder, the absolute value of it, will be equal to s minus s sub n, which is going to be less than or equal to b sub n plus 1. 3 says, in all cases we use the Taylor's inequality. And this is talked about on page 762. This is also called the remainder estimation theorem or Lagrange error bounds. So make sure you know all the wording that we have for this. And so this says if the absolute value of f, derivative of n plus 1 of x, is less than or equal to m, for all t between x and a inclusive, then the remainder r sub n of x of the Taylor series satisfies the inequality. The absolute value of r sub n of x is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. So m is an upper bound on the absolute value of f to the n plus 1 derivative of t on the interval from x to a. So right below this we have an example. The example says to estimate the magnitude of error involved in using the sum of the first 5 terms to approximate the sum of the entire series. And again, it does tell us the first 5 terms. So our sum is from n equals 0 to infinity of -1 to the nth power times 1 over 2 to the nth. So the first thing is that we have is b sub n is going to be equal to 1 over 2 to the nth. And the first thing that we know is that this is decreasing. So as our terms increase, we're going to be dividing by a larger value, and that would mean it's decreasing. 2, if we take the limit as n approaches infinity of 1 over 2 to the nth, we do arrive at 0, so those are both checks. Then we need to look at the series that we have, the first 5 terms. And so expanding this out, we have 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16. And then this keeps going, 1 over 32 plus 1 over 64, and I'll just put ... It does continue on. And so the first 5 terms that we have are from 1 to 1 over 16. So these are our first 5 terms, which is what it was asking for up here. So first 5 terms. As stated up above, we can see that then our remainder, the absolute value r sub n, is going to be less than or equal to b sub n plus 1. So back down to our problem. Since this was asking for the first 5 terms, b sub n plus 1 would be the next term, which is going to be that negative 1 over 32. Again, we are going to be taking the absolute value of that, but this is going to be less than or equal to b sub n plus 1, which is going to be the absolute value of negative 1 over 32, or just 1 over 32. And so this would be estimating the magnitude of the error. The next example right below, so I'm going to go ahead and circle, and we'll look at this one together in class. And then at the top of the next page, it says use the Lagrange error bound to find the upper bound on the error if the fifth polynomial, so t sub 5 of x, equals 1 minus x cubed over 3 factorial plus x to the fifth over 5 factorial is used to approximate sine 3. Is this the best method for finding the error? So the first thing that I want to note is that up here, as expanding this, our value that was circled out would be equal to 0, so it's the Maclaurin series. And so we are looking for using to approximate sine of 3. So since we have the fifth polynomial, our Taylor series polynomial, we're going to be looking at the absolute value of our remainder when n is 5 of our x value, which in this problem is 3. So we have n is equal to 5 and x is equal to 3. And we know that from the Lagrange error bounds, which is listed on the previous page, this is going to be less than or equal to m over, and then we have dividing this by n plus 1 factorial, and again n is 5, so we have 5 plus 1 factorial times, and then we have the absolute value of x minus a, and our a value in this is 0 and x is 3, so 3 minus 0 raised to the n plus 1, so 5 plus 1, and so this will be equal to m over 6 factorial times the absolute value of 3 raised to the 6th power. And what we need to find now is m, and as stated on the previous page, m is going to be the upper bound of the n plus 1 derivative. So we have the absolute value of f to the n plus 1 derivative of x. The absolute value of that is going to be less than or equal to m. So on the interval from x to a, so in this case it's going to be from 0 to 3. And so we need to find, since n is 5, we need to find the 6th derivative of x, and this will be less than or equal to that value m. So let's find the 6th derivative. So our original function f of x is going to be sine of x, and then we have f prime of x, second derivative, third derivative, fourth derivative, fifth derivative, and then we can find our 6th derivative. So writing these all out, first derivative is going to be cosine of x. Second derivative will be negative sine of x. Then we have negative cosine of x, sine of x. Fifth derivative is going to be cosine of x. And then our 6th derivative is going to be negative sine of x. And so we know that sine alternates between values that are between negative 1 and 1 and including those values. So for this problem, I would say that the absolute value of negative sine of x is going to always be less than or equal to 1, since we know that those values of sine of x would be between negative 1 and 1, including those values, those endpoints, and so it would be less than or equal to 1. And so this means that I would select our value of m equal to 1. So back up at the top, I would have 1 over 6 factorial times 3 raised to the 6th. And then substituting this into a calculator and working it out, I'm going to round 4 decimal places, and I get a value of 1.0125. So the remaining examples that we have in the notes for 11.11, I would like for you to circle, and we will look at these ones together in class.